So what I'm going to talk about today is work that we've been doing trying to synthesize recent developments in the area of deep learning approaches, really kind of trying to leverage that for applications in scientific computing domains. So I think, as you know, this audience is very well familiar with, there's a lot of unique sort of challenges for doing that in a way that's sort of reliable, robust, etc. Primarily focus on methods for modeling nonlinear dynamics. There's often a lot of requirements that are important that go well beyond just achieving good test accuracy. So, you know, you want, for example, models that, in the case of dynamics, would have stable long-time behaviors so they can be used as simulators. You want models that, you know, adhere to various, you know, physical principles like conservation of mass, conservation of energy, and so on. So I think there's, again, these tremendous opportunities to leverage these techniques, but there's also a lot of work that still needs to be done to really get these things into a form where they can be used reliably in these kind of simulation contexts. And so I'm just going to tell you a little bit about work we're doing in that direction. A lot of this is kind of recent work. I'll kind of talk about a subset of it, and I'd be very happy to talk with people that are interested in these techniques offline further. The key challenges that we often have to grapple with is we don't have, you know, pristine data when it comes to higher fidelity simulations, right? Simulations are often done at different levels of computational resolution. And so there's going to be all kinds of interesting artifacts that one has to overcome in that context. In the scientific and engineering context, we want to try to develop machine learning methods that learn representations that ultimately have some level of interpretability, and related to that allows us to incorporate inductive biases that would help make these methods more reliable for things like use as subgrid simulators. So anyway, there's lots of things I could say about this. Just as a quick summary, I think there's some tremendous opportunities here for developing theoretical foundations, really leveraging these nonlinear approximation approaches, which are somewhat novel in the deep learning context, you know, figuring out sort of what the key factors are for generalization, and then also just from what I think will emerge over time, and something we're also very interested in, is trying to figure out good metrics for success and failure in this context. So just as a quick summary, there's really this kind of need for combining all of these exciting and recent developments in machine learning community with a lot of the principles been around for quite a while in the scientific modeling and simulation communities. And so I think there's some really big challenges there, but also some great opportunity. Discuss some techniques that we've been developing for learning representations of nonlinear dynamical systems. And I'll kind of talk about two main strategies for doing that. One is going to essentially be a way of learning nonlinear state space models, essentially by using what are known as variational autoencoders, which we modified for doing dynamics, as well as ways to incorporate inductive biases. In the case of dynamical systems, you know, if you do qualitative analysis of dynamics, you often know a lot about the topology and geometry, and so we have some techniques for incorporating that into the learned models. And then the second set of methods I'll talk about will be for learning stochastic dynamical systems. So there you have to grapple additionally with the issue that the dynamics is inherently noisy, and then we have methods there to essentially learn stochastic models, essentially stochastic differential equations for modeling observations. And this is all going to be done at the level of samples as opposed to things like maximum likelihood estimates. So I'm going to talk about how we can leverage adversarial learning strategies for that. And so there's some close connections with generative adversarial networks. So just to kind of give some larger context in which we're trying to learn these representations, the overall setup is that there's some type of system dynamics that we're interested in. Again, it could be an experimental system or some higher fidelity simulation system that we're trying to simplify or coarse grain for the purposes of gaining computational efficiencies. And so what we basically have in hand is some type of observations. These are typically very high dimensional data sets. It could be fluid fields, could be other types of measurements. And we're essentially trying to perform a form of model selection. And we're going to use the predictions of the model. They could be the observables of interest as feedback essentially in that process. And, you know, I should just point out there's been a lot of methods developed for this purpose that have been applied quite successfully, especially in areas like aerodynamics. So one method would be proper orthogonal decomposition. The basic idea here is that you would take snapshots of the flow field. If you want to create a reduced order model, the way you would go about doing that is essentially looking for those modes in the system that vary the most, which amounts to essentially a principal component analysis of this sort of point cloud of spatial fields. And from that, then you can, you know, by doing your eigenvector eigenvalue analysis, pick out those dominant modes and kind of project the dynamics down. And so that works well for certain contexts. I will note that it's a linear model, and much of this ignores kind of the dynamical components, right? That could have been equally applied for snapshots in any permutation. So there's been some more recent developments where the dynamics is taken into account, where essentially, instead of just learning the snapshots, you basically learn a best linear model that would take some collection of snapshots that you have and allow you from snapshot X to predict state or behavior of the system would be at some time step, let's say t plus tau. And so this is known as dynamic mode decomposition. And this has also been successfully applied for a lot of fluid mechanics problems as a way to get reduced order models. Now, with both of these techniques, there's a lot of challenges. If you just think intrinsically about how the approximations are built up, this is essentially using the principle of superposition to build up the state of the system. And so if you had something like a translating observable in the system, that would require many, many modes in order to build up the superpositions. So there are many systems where this will work well if there's something like Fourier modes, and maybe most of the Fourier modes decay rather rapidly. But in systems that are kind of this more advective nature, techniques like this often require a lot of fundamental modes to capture the underlying behavior because of that superposition approach to approximation. There's also been some more symbolic ways of building up your representations for the dynamical system. These are known as dictionary methods, or SDYN is one popular technique. And basically the idea here is you'd create a symbolic library, linearly combine those functions that are in the symbolic library over your observables, and to try to get a compact representation, you would use something like an L1 regularization. And so again, that can work well in certain contexts, but this requires in advance that you kind of know a rich enough dictionary to be able to capture the dynamical phenomena. And there's also, while this might be more interpretable, you also have to caution a little bit the interpretation, because there could be issues of identifiability. And again, this is using kind of a linear superposition type of principle to build up approximations. So again, all these methods have had a lot of success and done quite well, but there are a lot of problems for which these techniques don't perform ideally. And that's where I think there's some real opportunities to leverage some of the unique approximation properties of things like neural networks and some of the training approaches that have been emerging in the deep learning community. So there's a lot of challenges we would need to address. One is, we want to learn stable dynamics that's not just capable of recapitulating the training data set of observations, but also of allowing us to perform much longer timescale simulations in a stable way. And so I'm going to talk a little bit about some strategies to do that. We obviously need to have some robustness if there's noise in the training data set, because the data is often not pristine. And as I was alluding to before, ways of incorporating various types of physical principles and information. I just wanted to mention some of these techniques just to kind of give a larger context in which we're working. So I'll talk first about this approach based on variational autoencoders. Basic strategy to try to enhance robustness and some of the statistical power in the data is that we're going to try to use the encoder framework in order to take whatever our observables are, something like that as fluid dynamics fields, and really try to extract what the essential state information is. And that's what I'm denoting here by Z. And the idea is to evolve in the latent space, in this much lower dimensional space, the state of the system, and then to recapitulate whatever the observables is. And in this way, in some sense, we're kind of filtering out the non-essential information. And really, this is a way in which we can focus on developing models that reproduce primarily the quantities of interest for the particular problem at hand. And so this will have a number of advantages with respect to stability, and also possibly even give us some insights into underlying dynamic mechanisms. And so the goal is really to try to develop these kind of representations where we can work in as low a dimension latent space as possible. Again, that'll have advantages with respect to filtering out noise, statistical power, and so on in the system. But the challenge, of course, is to learn this in a way where these intrinsic low-dimensional representations adhere to nice principles, like they're, have continuity in the representation, maybe even follow prescribed dynamical laws if we know something about the system and that it can be canonicalized. And so the approach that I'm going to take to do that is to leverage these recent developments in what's known as variational autoencoders. So these are going to be a little bit different than just doing a standard kind of neural network encoder where you have an encoder, let's say multilayer perceptron, and a decoder multilayer perceptron. We're going to introduce noise into the system as a regulatory mechanism. So I'll kind of walk you through a little bit what that is. Here's just a quick sketch of the neural network architecture for VAE. And so the idea here is that if I have some input field, as I'm showing up here on the upper right, the encoder would be whatever neural network architecture you want to use. It could be a convolutional neural network, multi-layer perceptron. But what's novel is that the information you extract from the input is used not only to give you an encoded state Z, but you also have an encoded standard deviation. And so you can think about this for now just being a fixed hyperparameter. And the idea of doing this is that an encoder is going to map not to a single state in latent space, but in some sense to a small probability distribution. And then what we're going to do on the latent space is we're going to have a prior that's essentially going to say whatever the representation is, we're going to have that it not deviate too much from some particular distribution, like, for example, a Gaussian, as a way of kind of setting a characteristic length scale to kind of pull all the latent codes together so that in conjunction with this little blobbing out, the different codes will have a little bit of interaction with each other. And that way, when the decoder needs to decode Z, it has to hedge its bets a little bit because of the potential overlap. And this will ultimately lead to a much more continuous representation than if we had done just sort of standard MLP maps. So that's going to be our strategy for gaining representations of the dynamical system. And I'm going to show you a few things that we also do in the dynamic context to include some additional regularizations that will allow us ultimately to do multi-step prediction. All right, so that's a really quick sketch of VAEs. If you're not familiar with them, they basically use probabilistic encoders and probabilistic decoders along with a prior on the latent space to kind of pull all of the latent structure together to help basically set the scale of the latent representation as well as imposing these continuity conditions. So the details are as follows. There's going to be a loss function, which we minimize, that has these three components, and I'll kind of go through in a little more detail in a moment. There'll be a reconstruction error term, which I'll tell you about in a second. That's basically going to be given the input U, going through this whole process here, how well did I predict the observable t plus tau? There's going to be this Kullback-Leibler divergence term, which I'll give you the mathematical details in a minute. That's basically going to be very similar to almost like a Bayesian prior on the latent space, saying, well, we'd like the probability distribution of latent codes not to differ too much from some prescribed distribution. And then I'm going to introduce this additional reconstruction regularization term, which is not in the standard VAE, but you'll see that it'll play an important role for our dynamic VAEs. And what this will do is say, not only are we going to predict the future state correctly, but these latent codes will also have to retain enough state information that I can also reproduce the inputs U that I had. And if I simultaneously impose those two conditions, that you extract into the latent representation ability to recapitulate the current state as well as predict the future state, this is really going to be key to get alignment so that I can do multi-state prediction. In other words, I can predict multiple time steps into the future, and ultimately with a little other considerations, I could also end up with now a simulator to do long time prediction. So I'll just say a little bit more on the next slide about the mathematical details. You have a probabilistic model that traces through what I've just drawn down here schematically. And what we're going to do is fit the data using essentially maximum likelihood estimation. So for the inputs xi, which were the system, the dynamical system at time t, and capital X, which will be the system at time t plus tau. And we're going to do that by tuning the parameters of the encoder, the probabilistic encoder, probabilistic decoder, and whatever the model is for the dynamics on the latent space. For now, I'll take the dynamics to be prescribed, but that also could be a neural network map, which maps the latent space back to a copy of itself. And so if you were to use the method of maximum likelihood, you'd basically be minimizing a log likelihood of the probability under the model for the joint distribution, little x and capital X. Now, what you do in variational inference to make this problem a little bit more tractable and to deal with that issue of having this probabilistic encoder is we have a model for what the probability distribution is on the latent space given the input. And that's what this Q theta of Z given X is. And there'll also be a probability distribution for the decoding step. And what we're going to do is use the evidence lower bound as a lower bound on the maximum likelihood in order to do our model selection. And so if we do that, you can derive that this likelihood can be split into two terms, a reconstruction error, which I'll just show you here, reconstruction error would be given by this expectation under Q theta of the log probability of xi given z. And there would be this Kullback-Leibler divergence term, which would be given by when beta equals 1, how far this probability distribution into the latent codes differs from the standard Gaussian. So putting those pieces together can get a lower bound estimate on the maximum likelihood, which when maximized, by the way, if we had access to all possible functional forms for Q theta, would recover the likelihood. Now, what makes this variational is that the Q theta E here is not actually going to be able to cover the entire function space. It's going to be something like a neural network representation ultimately of that probability distribution. And so the evidence lower bound provides then a variational lower bound given that approximation. So this provides a very nice and convenient way for us then to compute this loss function. And we would do that in practice by using empirical samples of this Q theta distribution, which we have in hand to estimate each of these terms in the loss function. All right, so intuitively, the reconstruction error is what you would imagine. It's essentially trying to maximize the overlap of the decoder with the predicted snapshot, and the Kullback-Leibler divergence is serving to regularize how things are going to be ultimately organized in the latent space. We're going to modify this for the dynamic context two ways. One is we're not reproducing the original input, hence I've used this capital X and little x, capital X being the snapshot at time t, and little x being the snapshot at t plus tau. And secondly, what we're going to do is introduce this additional reconstruction error, require that the latent code have the ability to predict the original input as well. So putting all that together, then, this provides a framework for learning representations in a much lower dimensional latent space of the dynamical process. Let me show you how this works for the Burger's equation. This would be an example of a nonlinear PD. And we're going to look at it from this point of view of kind of parameterized PDs. In particular, I'm going to look at a rather specialized case, which is we have initial conditions that essentially have one parameter associated with them. So what this is ultimately going to amount to is kind of this 2D manifold in the function space that evolves. And importantly, because the dynamics is nonlinear, that has some interesting geometric structure, which provides some challenges if you were to try to apply something like dynamic mode decomposition or POD. So here's just the initial family of functions that we're going to be considering the responses of and trying to learn this kind of reduced dynamical model of. So the Burger's equation I'm going to be dealing with also will be the viscous Burger's equation. Now, the reason why that's a good benchmark problem is if you know about the viscous Burger's equation, you can use the Cole-Hop transform to ultimately transform that through a nonlinear process into a standard diffusion equation. And so this would provide a nice basis to make comparisons of our methods with, because, you know, one way you could try to get a reduced order model is simply truncate the Fourier expansion after doing the Cole-Hop transformation. And so we're going to see, you know, with a comparable number of modes, how the VAEs behave relative to something like this, this analytic strategy, and also compare with some of the other methods. I'll mention also, because of this existence of this nonlinear transformation, we know a priori that at least there's some representation in the latent space where the Burger's equation dynamics could be represented essentially by an exponential decay. Because if you look at how the eigenmodes of the diffusion equation behave, especially if you truncate it, that's essentially going to be an ODE that decays like the usual exponential, according to the rate being whatever the eigenvalue of the operator is. All right, so based on that, our approach is going to be to use VAEs, where we, you know, learn the encoder decoder. For now, I'm going to prescribe the latent space dynamics just to be exponential decay. So the job of the VAE then is to organize the dynamical system and its representation in such a way that we, in the latent space, have an exponential decay, but at the same time have the capability to reproduce the observables. All right, so that's the basic benchmark problem that I'm going to tell you a little bit about. So we minimize the loss that I showed you on the previous slide. So if I did not have that reconstruction loss, if we just did a standard variational autoencoder without really taking the dynamics into account, what you would have is a latent representation that looks like this. So in the orange direction, I'm showing time, and the blue colors are basically showing as I go from alpha 0 up to alpha 1. And so you get these kind of semicircular arcs for the family of functions, and the dynamics is happening in this direction because we've prescribed in latent space that we want the dynamics to be represented as some type of exponential decay. So because all the training was done essentially with single step prediction, what you will end up with is mappings from, you know, these initial conditions to the first step. But you can see that if I look at what the second step is, that may get mapped to a different latent code, because the only information in the standard VAE would be that I could make the prediction of the next time step. There's nothing indicating that I have to be able to reproduce the current input. So you get this kind of mismatch, and obviously that's very problematic towards that goal of having stable long-time predictors. And so our regularization really plays an important role in kind of sorting this kind of issue out in the latent space. And so in particular, we have that with the reconstruction regularization, we get this kind of representation. And so you can see that the initial condition is this outer arc, and then the first time step is this inner arc. And then now when we go to make the time step prediction from the second state to the third state, you see that now everything is aligned. And so now we can do multi-state prediction, as I'm showing here, by just composing the learned dynamic VAE. So this is just making some comparisons with dynamic mode decomposition. You can see it struggles a bit to be able to build up the evolution of this particular solution under the Burger's equation using just superposition of a few modes. VAE, as you see, can, because of that nonlinear approximation capability, essentially you have a lot of model capacity built into deep neural networks, can really make quite accurate prediction. We also wanted to see if the nonlinear approximation properties were really playing an important role. So we did a version of VAE where we essentially just use linear models for the encoder and decoder. And you can see, again, it struggles to give appropriate predictions for some of the inputs. This is just showing some quantitative results. And so you could do a comparable reduced order model using something like Cole-Hop with 2 modes versus this nonlinear VAE with 2 modes. And you can see that, it does not have a comparable level of accuracy. But, of course, if you go up to enough modes in the Fourier space, you can start to capture, obviously, the dynamics. And that's what's being illustrated here. You can also try it with and without the reconstruction regularization, and you really see the difference in accuracy under that multi-step prediction. So we've only trained on the time scale 0.25, and here I'm basically showing you what the 4 composed steps accuracy is. And so with the regularization, you see you do get quite a dramatic difference relative to without the reconstruction regularization. So we noticed in a lot of these simulations, like if I were to have that alpha parameter be periodic, the kind of structure that I want in latent space would essentially be like an annulus. That would be, the rings of the annulus would essentially be the dynamics at each time step. But when you train in practice, these kinds of representations, even though we know they're theoretically possible, often are very hard to access through training because of topological issues. So if I were really mapping to a 2-dimensional latent space, essentially the initial randomized neural network encoder and decoder are kind of entangled, and you're stuck in kind of a local minimizer, and it's very difficult to get out. So you would see something like this often when the intrinsic parameters, in this case the alpha, are, for example, periodic. So this kind of points to the fact that for many dynamical systems, there's going to be interesting topological information that either constrains the representation if there's a mismatch between our latent space and that topology, or something that we actually can exploit so that, for example, we need to train VAE in 3 dimensions, even though the intrinsic dimension was 2 because of this training issue. And so if we wanted to get something which was still intrinsically 2-dimensional, we'd have to take that topology into account. So I want to talk about some additional modifications where we've now developed techniques where we can have latent spaces with prescribed geometry and topology. And so without going through all the details here, essentially what we're going to do is develop a neural network architecture where you can still use backpropagation and many of the same approaches as the non-topological case, namely things like convolutional neural networks, multilayer perceptrons. And the way we're going to combine these techniques is we're going to allow for this epsilon theta to be essentially any neural network or any backpropagatable architecture that you're interested in. And the way we're going to map to these topological spaces is by using this technique where this map maps to some embedding space, and then we'll map it to prescribed manifold structure by solving this projection problem. So you can think about lambda as projecting the point in the embedding space to the nearest point on the manifold. And if we do things in that manner, we can formulate it in this way. But the problem is, of course, that won't directly be backpropagatable because there's an optimization problem now as part of the function pipeline. So what we've done is we've developed using essentially adjoint methods a way to backpropagate through this optimization problem. And so what we can do if we think about coordinates on the manifold, although these don't need to be prescribed, this is more just an analytic device just to illustrate the idea, because we'll allow for representations which are just general point clouds in whatever the embedding space is. You won't need an analytic representation of the manifold. So if you were to solve it in a particular coordinate system here, as I'm saying, U star, K star is just the chart index, U star being the surface coordinate, which gets you the closest point of the manifold to that point W. You can formulate this in a way that involves an implicit equation, namely minimizing this would be equivalent to finding the zero of the gradient of this capital phi k, the objective function. And so this implicit formulation actually allows us to swap the derivatives off from the actual map in lambda contracted with the gradient to tilde 3 into a final result, which will get us the equivalent value of that theta. Essentially, we'll do it instead of using this expression on the right, we can use essentially Jacobian and gradients of the implicit problem G. And so that's what we do here on the right. I won't go through all the derivations now. I'll just can look in our paper for the details. Essentially, what this allows us to do, though, is to compute this gradient in this manifold map, basically propagating the appropriate gradient information through this optimization problem. All right, so this is what we call the geometric dynamic VAEs. And this really allows us to overcome that obstacle that there could be a mismatch between the latent space and the topology of the underlying dynamical system. Or rather than using extra dimensions, we can make the latent space of a lower dimension by taking that topological information into account. And also mention this can be used not only for orientable manifolds, you can use it pretty much for any arbitrary type of manifold. And that includes the unorientable case. And I'll show an example, a Klein model, just to kind of illustrate that idea. But essentially, you can build up your latent representations using any space you like. The most typical way you would do this is by having a product space of interesting topologies to encode various information about periodicity or other qualitative analysis information that you have about the dynamical system. So this is now going to show how we can do Berger's equation when we have periodic and doubly periodic parameters. These would be some natural ways to try to represent the dynamics. Again, if we kind of just did a standard autoencoder, you would have to go to high enough dimensions that that map can kind of untwist itself. This is just showing an autoencoder in 3 dimensions. Whereas if we get lucky in the training protocol, sometimes you can get it to work in 2 dimensions, as I'm showing here on the right. Ideally, you would like representations that look something like this, because it's periodic. Essentially, this should all be able to be mapped to a cylinder, where the axis of the cylinder is time and the radii is the alpha periodic alpha parameter. So it's all about specifying how you would like the machine learning methods to kind of organize your state space information. And so this is just showing quick comparison between our GD-VAEs methods, standard variational autoencoders without any geometric priors, and standard autoencoders with and without geometric priors. And so you can see, again, for multi-step predictions, this really helps quite a bit to stabilize things, gives you a very low-dimensional representation of those dynamical systems. You can similarly do that for the doubly periodic case. In that case, you're effectively mapping to the surface of a torus, although I'll caution you wouldn't do it to a torus in 3 dimensions. We actually do this for a torus that's the Clifford torus in R4, what's known as the flat torus. It's just a product space of 2 circles. And that works actually quite nicely to capture the behavior and multi-step dynamics of this doubly periodic parameterized PD. You can use this also to represent various types of constrained dynamical systems. So this will give you a nice representation. Again, that could be very useful in various types of optimization settings and so on. Instead of having to solve auxiliary equations to impose the constraints, once you kind of have this representations, you can use that in a larger outer loop optimization, for example. So here's just a little example of a actuator arm. If I constrain the lengths to be fixed, I'll end up with something like a torus, but you can also have more exotic types of constraints. So I did one where essentially the points have to live on the surface of a Klein model. And again, the geometric dynamic VAs can learn some nice representations in both of those settings. We've also pushed this to spatial fields. In particular, this is an example of a brusselator where by qualitative analysis, we know this settles down to a limit cycle. So if we want to represent the behavior of the dynamical system essentially on the limit cycle, for these 2-dimensional spatial fields, we've developed techniques for doing that, essentially using convolutional neural networks and transposed convolutional layers, which shown here. Again, we've prescribed the dynamics on the latent space, and then the job of the neural network is to kind of organize things so that that prescribed qualitative analysis, if you like, canonicalization of the dynamics can be realized in practice. And this wouldn't require any knowledge in advance of the underlying PD. This could be done from experimental data or higher fidelity simulation data. So this is just showing what the predictions are of the GD-VAE versus the actual solutions of the reaction diffusion PD in that context. So you can see it works quite well. And so we have a software package for this for people that are interested in utilizing either just the manifold latent space part, or if you want to use the full geometric dynamic VAEs pipeline. All of that's been put together in a Python package, which you can find on our website here. And I'd also be very happy to talk offline more about that. So that's one of the techniques that we're working on in order to kind of encode state space representations of dynamical systems. Primarily, you'll notice this has been for deterministic dynamical systems. So the other thing that I'll talk about in a set of methods is ways to learn representations for stochastic dynamical systems. And so what we're really going to leverage here are results from generative modeling and recent results in things like generative adversarial networks. And so just as two example problems, the first one I'll go over and show some results on is this kind of system identification problem or learning of a physical model where we have some trajectory data and we have some inkling of what the mechanics are, but we'd like to estimate parameters like the stiffness, damping, and temperature. So you can think about this inertial Ornstein-Uhlenbeck process, which intuitively amounts to essentially a bead spring system with those unknown mechanical parameters. The other one I'll also show some results for is a coarse graining problem where we have a particle system with an unknown force law, and we'd like to learn from the dynamics, essentially a representation of the forces by looking at the particle trajectories. And so we'll represent them, the force law, by an appropriate neural network. So there's lots of challenges of doing that in practice. One of them is the traditional way you might go about doing that is to use things like maximum likelihood estimation, but then that requires you to compute rather expensive likelihood estimators. Using likelihood alone may not be prone to introducing certain inductive biases. So I'm going to show you an alternative formulation that essentially uses adversarial training methods. So I'll walk you through real quick how generative adversarial methods work from kind of a mathematical perspective, and then I'll show you what our extensions are to model these stochastic dynamical systems. And so the idea in these generative approaches is to use implicit generative methods where we never actually construct the probability densities. What we're essentially trying to use neural networks or other model classes for is to learn a sampler that would sample from some target probability distribution. In particular, the underlying probability distribution which generated the training data is ideally what we're trying to target. What we do in adversarial approaches is use a purely sample-based approach, so there will be no likelihood functions involved. The way we're going to do this is essentially by formulating what amounts to a two-player game, where you can think about the weights and biases in the neural networks, the model parameters, as being the strategies. And these two players are essentially in an adversarial game where the discriminator and the generator have the following roles. So the generator, as I mentioned before, is going to generate training data samples. The discriminator's job is going to be to take samples both from the generator and the discriminator and try to distinguish the extent to which they are different. If the discriminator cannot tell the difference between the sample set that you generated versus the training set, then that would be considered a success. And so what's going to happen in practice is we're going to try to solve this two-player game so that the generator essentially follows gradients that can generate samples so well that the discriminator cannot make this distinction. So the discriminator, most naturally, the original formulation was to use something like a binary classifier. And essentially what it's going to do is try to estimate the probability whether or not that sample came from the training data or whether it came from the generator. All right, so that's going to be the key idea, and that essentially is replacing that Kullback-Leibler divergence that you have in maximum likelihood estimation instead with this two-player game. So it's going to provide some alternative gradients, metrics, divergences in aligning the implicit generative model with the underlying empirical data distribution. Just to give you a little bit more mathematical detail, the way that you formulate these techniques is you create what I call a synthetic labeled data set, which is going to be a mixture of samples that come from the generator and samples that come from the training set. And we'll do that in 50-50 proportion. And we'll put labels 1 on the data from the training data, and we'll put 0 labels on those samples that came from the generator. And then the job of the discriminator is to try to estimate this underlying idealized probability, which is what is the probability that that particular data point should have the label 1. And then 1 minus d can be interpreted as the probability that you should assign the label 0 to a given point. The way you would ideally do this classification to minimize the 0-1 loss, in other words, make as few mistakes as possible, is you would use the Bayesian classifier, which basically picks a label that has the highest probability. Now, of course, these things are not known to you in advance. These are things you have to essentially obtain through your training protocols. So just to give a little bit more detail, you can look at what the probability distribution is of that synthetic data set that I just mentioned. That's given by this expression here. It's basically just a mixture distribution of the data distribution and the model distribution. The joint distribution on samples and labels is given by what I've written here, where these are just characteristic functions for when y equals 1 and for when y equals 0. So now if you were to look at what is the probability of this synthetic data distribution having a label 1 assigned to it, given that the sample was x, you can easily compute from here the conditional probability, and it comes out to be that. So what you notice immediately is that if my data distribution and my model distribution were equal to each other, this would come out to be 1/2. So essentially a value of 1/2 is when the discriminator is maximally confused, and that's in some sense what the goal of the generator is. So putting this all together, you can formulate a loss function both for the discriminator and the generator as follows. We're going to use the cross entropy loss to try to, from the empirical samples, estimate what that probability is, d of x. That would amount to the method of maximum likelihood for the classifier. And if you work it out for what the synthetic data distribution is, that's this expression that I'm showing here on the right. And then there's an additional term that depends on the generator distribution. I won't say too much about that. That's essentially an entropy term that one could also incorporate into this. So it's really these first two terms, which is the primary part in estimating the discriminator probability. Again, that's just the cross entropy loss, trying to minimize the classification error and assigning those 0 and 1 labels. So you're going to minimize this in order to try to get your discriminator model. And in the ideal world, you would get the Bayesian classifier. And now the generator's job is to try to make the discriminator's loss as big as possible. So for a given choice of the discriminator, the generator is going to try to maximize that loss, whereas, of course, the discriminator is trying to minimize that loss. There's also variations of this to avoid vanishing gradients and so on. I won't say too much about that, where you can modify the generator's objective function. But for now, I'll just stick in the zero-sum game setting. So what happens if you actually were to solve for the discriminator to its optimum and plug it into the generator? What would be the objective function that you're ultimately minimizing? And so you can go through this analysis, and you can actually show that if I use the optimal discriminator, that is that optimal probability, d star of x, which would be given by p data of x over p data of x plus p model, namely, if I knew the conditional probability of y equal 1 given x directly, plug that into the model, then what kind of learning signal would that be giving back to the generator? Well, if you go through this analysis using that synthetic data distribution, you can actually work everything out analytically, plug this into the loss as I've done down here, and when you work it all out, you actually realize that this is going to be this averaging of the Kullback-Leibler divergence of p data with respect to the average distribution plus 1/2 p model with respect to the average distribution. So this is a well-known divergence. This is known as the Jensen-Shannon distance. And so what you're essentially doing through this training protocol, if you were able to do all of your optimization perfectly, is you would be minimizing for the empirical distributions of the generator and the underlying training data, you'd be minimizing this Jensen-Shannon distance. So that's what's driving all the training of the generator towards the underlying empirical measure of the training distribution. So in practice, this has some challenges, and I'll just show you real quickly that you often end up with issue of not being able to do the optimization exactly. You end up with this oscillations. So this is just showing a very simple example where the target distribution is a Gaussian. And here I've used as input noise a uniform random variable. Of course, if I had used the Gaussian, that would be pretty trivial to learn. But this is often the kind of scenario you have in practice. The driving noises, you don't necessarily know how to align those with the distributions that you're ultimately trying to compute, especially if you're trying to do something like learning that coarse grain model of that stochastic dynamical system. The neural networks often have to contort themselves to create that final probability distribution. And when you're doing this alternating maximization, minimization, you can end up with oscillations. This issue even becomes more severe if you go out of the zero-sum game setting and you're more in the setting of like a Nash equilibrium. It's well known that these kind of alternating maximum, minimum relaxation problems are very, very prone to various types of oscillations around the game equilibrium. So what we're going to do is formulate an alternative to that to avoid some of these training issues, and also to allow for some more inductive biases to account for some of the dynamical properties of the underlying data. But I want to give you a little bit of a mathematical perspective on traditional GANs. So I won't go through everything here. Again, I'll kind of refer you to the papers. The main takeaway is that for these dynamical systems, there's a lot of probabilistic structure in the samples that we're generating. So if we were to just naively apply the standard GANs with trajectory fragments, we really wouldn't get coverage in the probability space. And as a consequence, we wouldn't get very good training. So what we're going to leverage is the fact that in our random variable, there's actually a lot of dependencies between the components. In particular, if I think of something like the Langevin dynamics integrated with something analogous to like Valore integration, you're going to have that the current state depends on the previous two states, and that's going to occur essentially through a recurrence. And so you can think about that in terms of what's known as a graphical model. And so we're going to exploit that structure when we formulate our generative methods. Also, with respect to the discriminator, there may be observables that we can use that would greatly accelerate training relative to just using Kullback-Leibler divergence between the empirical distributions. And so we're going to leverage those two aspects of reformulation of the method, as well as learning over model classes, which are not just general recurrent neural networks, but rather stable stochastic M-step methods. And so you can think about the model class for the implicit generator as coming from a stochastic multi-step method with unknown parameters P. Again, this can still incorporate neural network components, but we're going to do it in this larger kind of framework of numerical analysis. And we'll also allow for the initial conditions to be unknown. All right, so I'm going to tell you how we're going to put those pieces together. And we're going to replace that Jensen-Shannon loss with what's known as maximum mean discrepancy or generalized method of moments. And this will provide a way for us to introduce more inductive biases into the training protocol that can take into account physics, observables of interest, and so on. All right, so I'm not going to say too much about this. You can also train the GANs in different ways depending on how you make use of dynamical information. You could either use the conditional distributions or the marginal distributions. I'll show you some comparisons of those different training protocols and kind of refer you to the paper for more details on that. A quick overview of how we're reformulating the generative model. If I had two empirical distributions, one for the generator, one for the training data, the loss that we're going to use is going to be integral probability metric. This provides a stronger signal back to the generator. This includes things like the Wasserstein distance, if you were to use one Lipschitz functions, for example. The strategy we're going to use is to have test functions here that compare the two random variables and basically try to find how they maximally different by using f, which is within a reproducing kernel Hilbert space. And we'll just make the requirement that f has to have at most unit norm. And so if we do that, that allows us to introduce inductive biases through the kernel that generates that reproducing kernel Hilbert space. And then by introducing these two embeddings, the measures P and Q, namely through taking expectations of the kernel, we can reformulate this integral probability metric. I'll just kind of, in the interest of time, summarize down here to effectively looking at the difference in the reproducing kernel Hilbert space of the embeddings of those two empirical distributions. So in many ways, this is like a kernel density estimator, or you could think about it as a moment method where we're basically comparing some generalized moments. And the differences between those generalized moments is what we're going to use ultimately to drive the generator towards alignment with the empirical data distribution. We use these unbiased estimators to achieve that outcome. I realize I don't have a lot of time, so I'll refer you to the paper for a lot of the technical details. These particular loss functions, while we don't have to solve now the discriminator step explicitly because we've done it analytically through that integral probability metric solution, when we're trying to do stuff like stochastic gradient descent, we now have to grapple with some new issues. For example, second order statistics in the loss function, as well as having to backpropagate through the trajectories of the stochastic dynamical systems. So I'm not going to go into a lot of detail of that because of the interest of time here, but we've developed methods for doing that, essentially based on adjoint approaches, and I'll refer you to the paper for all of the details of that. And what I wanted to spend the remaining time on is just saying a little bit about some results with these techniques, and we'd be happy to talk more about some of this offline. These slides that I'm kind of skipping through are the gory details of how you actually compute gradients of that MMD loss with trajectory data, exploiting, again, the graphical structure of the underlying random variables. So let me just show you some results in the remaining few minutes. So the first one I mentioned was on learning models for dynamical systems. In this case, I'm doing this inertial Ornstein-Uhlenbeck process, and I want to learn effectively the damping, the stiffness, and the thermal parameters. And I'm going to do that from observations of the trajectories. All this is sample-based. There's no maximum likelihood estimation involved. It's I have samples from the generated M-step stochastic process. That's my generator, which I compare with samples of the numerical simulations. And so this is a collection of behaviors. What's really important to note here is some parameters are going to be sensitive on different timescales. So on very short timescales, there might not be a lot of information about, for example, the damping, because that may be dominated by kind of thermal fluctuations. And on the long timescales, it may be that stiffness and damping dominate relative to things like thermal fluctuation. So there's a really interesting question, I think, in a lot of these estimation problems in making sure that these sort of dynamical fragment windows are sort of sufficiently large and rich enough to be able to provide a learning signal for the underlying features of the system that you're trying to learn. And so in our method, we have a way of doing that through essentially downsampling the trajectory on a time scale tau, and all those backpropagation techniques that I developed will work perfectly fine in that downsampled setting, but it kind of reduces the dimensionality quite significantly of the trajectory fragments and those probability distributions that are either being compared on the conditional or marginal level. All right, so this is the data set, as I said before. This is some of the sample behaviors that you can obtain, and this is the actual outcome of training here. So these are the trajectory fragments that I was referring to a minute ago, and we have this method for downsampling the trajectory fragments, again, to try to get things into a lower dimensional setting so there's stronger learning signals by downsampling on time steps tau, even though the actual numerical and computational techniques are computing the dynamics on a timescale delta t, which would be the numerical timescale. So using these trajectory fragments, we're going to estimate these three parameters and the results that we get. Now, interestingly enough, if you were to do maximum likelihood and you try to estimate the temperature parameter, there's quite a bit of challenges with that because there's a local optimum where you can make data very likely by just increasing the temperature. The larger you make the temperature, the larger the likelihood is, simply because you get more overlap with the data. We see a similar trend here, but interestingly enough, once the stiffness and the damping parameters kind of get in the right ballpark, we get pulled away from that local optima and into the correct estimate. So these are just our results for estimating stiffness. You can see we can get that parameter 5% accuracy here. These are just the training dynamics over the epochs, going from 0 to 3000 here for one particular instance of training. The temperature is a little bit harder to pin down. We've noticed that in many of the training runs, we do get exactly the correct temperature, but under some of the runs, this issue where there might be misalignment, sampling error between the dynamical system and the training samples. And one way to make up for that is to increase your temperature. So we're only able to get that in the current prototyping down to about 50% accuracy. We are able to get good results for the damping. So again, what I think is significant here is we're able to estimate all of these parameters simultaneously for this dynamical system. And in addition, if you had some model for the observable noise, that could also be incorporated quite readily in this framework. I'll show you now an example where we're learning unknown force laws. Again, we're doing this in the context of inertial Langevin dynamics. So these are all second-order dynamical systems. You have to grapple again with that issue of high dimensionality, and we're really going to exploit the probabilistic dependencies to get a reduction in the dimensionality, which will increase the sensitivity in the learned model to the underlying trajectory data. So we're doing this again for these different training protocols that I mentioned on trajectory fragments. So just to give you an idea of what the training data looks like, it's basically observing fragments of trajectories along the lines what I'm showing here on the left. This would be the full trajectory. Obviously, we're doing it for many more. And so what we're going to do is have protocols that use the full trajectory from the beginning outward versus just using trajectory fragments, which I'm showing here on the right, just to give you a qualitative feel for how that behaves. And the particular underlying model here will be a radially symmetric double well potential. Obviously, we're working to apply this as well to more complex systems. So this is what the underlying force law looks like that we should be learning. And then we use an L1 norm to assess the accuracy of the model. So the L1 norm is never used in the training. It's done using that MMD approach that I showed earlier. This is just used to get our test errors at the end. And you can see learning the overall marginal probability distributions. And then this just shows, again, that point about we don't just want to be able to recapitulate the training data, we'd like to be able to simulate out the larger timescales. And so this is just showing on the left our learned neural network model, and you can see we can basically simulate that indefinitely, and it will produce the appropriate marginals, the appropriate equilibrium distributions, because we're essentially learning over a class of stable M-step stochastic numerical methods. We're not allowing this to just be a general recurrent neural network. We've built in some of those numerical properties into the underlying model class and architecture. And so here on the right is the target model, on the left now is simulations performed with our neural network approach using SDYN-GANs. Okay, so I think in the interest of time, that's probably a good place for me to wrap up, and I'd be very happy to talk more about these methods, potential applications. I'll refer you to our papers for a lot of the details, but I hope this gives you some of the things that we're working on here. Look forward to continuing those discussions. So thanks so much for your attention.